All right. Now we're going to move on to exponentials inverse, and those are called logarithms. For short, we call them logs. So we're going to do logs number 1 today. And first of all, a log function. So a log function is a log base b of a y value is x. So this is what a log function looks like. It's a log function because it has the word log in it. The log function is an inverse of the exponential. What that means is I can change a log to an exponent and an exponent to a log by a very slick transformation. And what that transformation is that the base kicks up and the word log goes away. So if I want to change log to exponential, the log has to go away because it's no longer going to be a log, so therefore the word can't be there. So the y value is the base kick up the exponent. This transformation from log form, exponential form, is a key component of what you're going to be doing with logs. You must be able to convert one to the other. So just the same way, if I have exponential, in order to change it back, I must have the word log. The base of the log is the base of the exponent. Base. This left side stays, and then the exponent drops down. So you need to be able to go in both directions, changing log to exponents, exponents to logs. You need to be able to go in both directions. It's a very highly key component to all of the things we do with logs. Solving them, simplifying them, changing them, everything. All right, a couple of properties that you need to know. The first one is that if I have a log base b of b, its value is 1. This will always be the case. If the base and the number are the same, the value of the log is 1. The reason for it is, back to this exponent rule. If I were to change this, kick this up, get rid of the word log, b is equal to the base kicks up b to the 1. That is true, because anything to the 1 is itself. So if they're the same, I'm going to get 1. All right, so the next one, the next property, if I have log base b of 1, the value of this is 0. Again, it goes back to the proof by using inverse, or the inverse exponential. 1 is equal to, because remember the word log goes away, b kicks up, b to the 0. And anything to the 0 is 1. So the exponential version proves the log property. These are properties that you have to know. All right, you're going to be asked to simplify logs using these kind of ideas. So basically what we want to know is what exponent on the base, because that's what's going to be over here. What exponent on the base gives me this other number? What exponent on the base gives me this number? So when you're asked log base 2 of 32, what exponent on 2 gives me 32? Until you get a better hang of it, you might want to set it equal to some value, x, some unknown, and change it. So 32 is 2 to what power? Well, 32 is 2 to the 5th. So 2 to the 5th, 2 to the x, if the bases are alike, the exponents are alike, this must be the value of 5. And if you think about it, what exponent on the base gives me that number? The exponent of 5 on 2 gives me the 32. So let's look at a few more. Log of 4 oh, sorry, that's the other way. Log base 4 of 64. What's its value? What exponent on 4 gives me 64? We'll come back to it. Here I have log 4 of 2. Log 7 of square root of 7. Okay, so on these, what exponent on 4? What exponent of 4 gives you 64? Those are things that you should know. But if not, you can convert it. This is 4 to the x, and this is 4 cubed. Therefore, it must be the value of 3. This whole thing has a value of 3. Log base 4 of 2. What's the value of this? Well, what exponent on 4 gives you 2? Well, only the square root of 4 is 2, so that must be 4 to the 1/2. Remember that in over out idea? So therefore, it must be 1/2. So what exponent on 7 gives you the square root of 7? Again, 1/2. All right, so we can use whole numbers, could be fractions. In general, a log is in base 10. 10 of, we'll say 0.01. If it's in base of 10, generally we don't write it. So when you see just log of 4 or log of 0.01, the base is 10. And the base is always written kind of like a subscript, lower and smaller. However, if you don't see it, it's a 10. If it's other than a 10, it has to be written in. So on this one, if I have log base 10 0.01, what exponent on 10 gives me 0.01? Well, that's 10 to the x is 1 over 100. So that's 10 to the x is 10 to the negative 2. So it must be the value of this is negative 2. So you can have negatives as well as fractions and whole numbers. But one thing you need to definitely be aware of is that the common base is 10. And we call that the common log base. Common log is base 10. So it looks like log 10 of x is the same as log of x. We just don't write the base 10. We have also the natural log. With the natural log, it's base e, because if we remember, the natural base is something we talked about back in section 8.3 with the e. So now the e is going to convert over with our logs as well. So the natural base of e, it would look log of e. However, we don't like this. We don't want log of e because we know e to be a very specific number. So we actually rewrite it as the ln, natural log. I don't know why they didn't go NL, but they wanted ln. Natural log is in the base of e. It's a given. Just like if you don't see log with a base, ln you're not going to see with the e. So you do not see log base e. You do not see natural log e. Just natural log implies the base of e. Just log implies the base of 10. LOG log and LN natural log have the exact same properties. So if I have natural log of e, remember the base on this is e, so its value is 1. If I have natural log of 1, the base on this is e, so the exponent is 0. Go back to the very beginning of the notes where we did these property logs. They work exactly the same for natural logs. Anything we do with LOG will work for LN. Always will be that way. So that's our first thing on logs, logs number 1.